Hello everyone. Today I am going to explain to you the mind map for atomic structure. So I am going to explain you with the help of this mind map. So from the starting I am going to explain the discovery of some subatomic particles. Okay, subatomic particles like electron, proton and neutron. Okay, so who discovered this? Electron. Electron is discovered by J.J. Thomson. And what is the charge on electron? Charge on electron is 1.6 10 raised to power minus 19 coulomb. Now, what is the mass of electron? Mass of electron is 9.1 10 raised to power minus 31 kilogram. Okay. Now, next, Ernst Rutherford. Ernst Rutherford has discovered proton. Now, what is the charge on proton? Charge on proton is this one, plus 1.6. You can skip 0 to 2 because that is not the whole value. Charge on proton is 1.6 10 raised to power minus 19 and mass of proton is 1.675 10 raised to power minus 27 kg, or if it is in gram, 1.67 into 10 raised to power minus 24 gram. Okay. Now the next one is James Chadwick. James Chadwick discovered neutron. What does that mean? Now neutron, charge on neutron is 0 and mass of neutron is same as that of proton. Mass of neutron is same as that of proton, that is 1.67 10 raised to power minus 27 kg. So we have covered all the three, means J.J. Thomson, charge charge on electron and mass on electron, and Ernst Rutherford discovered proton. Charge on proton is 1.6022 into 10 raised to power minus 19 and mass of proton is 1.672 into 10 raised to power minus 27. And the James Chadwick discovered neutron and the charge on neutron is 0 and the mass of the neutron is 1.675 into 10 raised to power minus 27 kg. So these three discoveries can be asked easily in the examination. Okay, now I am going to explain the Thomson atomic model, or watermelon model we can say, plum pudding model we can say. So these are the this is the first model that is discovered by the Thomson for the atom. So we have atom. Thomson said that atom is is circle and electrons are embedded in the atom like a watermelon. He said that a watermelon, like a watermelon, has all the red part, all the red part of watermelon. He took as proton, and the seeds of the watermelon he considered as electron. Okay, so this is Thomson atomic model. Thomson says that atom is electrically neutral. Electrically neutral means the proton and the electron are of equal number. Okay, so this is a Thomson atomic model. Atom possesses a spherical shape. it's round in shape, in which the positive charge is uniformly distributed. Means the positively charged is distributed in the whole atom and the electrons are embedded in it. And the electrons are embedded in it. Okay. So this is Thomson atomic model. But the story doesn't end here. Okay. After the Thomson, we got Rutherford nuclear atomic model. Okay. Now we are going to discuss its atomic model, its postulates and the drawbacks. Okay. Now we have this one, Rutherford atomic model. Rutherford did his experiment by a thin gold foil. Okay. He passed the alpha particles, means this is the uranium, and they surrounded by a lead chamber. Alpha particles are bombarded through this gold foil. Alpha particles are bombarded. Alpha particles are what? Alpha particles are 2-unit positively charged helium nuclei. Positively charged helium nuclei. Now, before further explaining this gold foil experiment, Rutherford gold foil experiment, I want to ask you if they are going to repel each other. Positive and positive are going to repel each other, right? Repel, and positive and negative attract each other. So I am going to explain this, the postulates of Rutherford atomic model by this. Okay, so Rutherford bombarded alpha particles from this gold foil. Okay, from this gold foil, and we have, suppose this is a ZNS, fluorescent material. This is the coating of the ZNS, fluorescent material. Means if something is going to strike over it, it produces a black type of scintillations. Okay, so the postulates of Rutherford are, first, the observations. Observations. What are the observations of Rutherford? Rutherford said that the alpha particles, most of the alpha particles goes in the straight line. Most of the alpha particles pass through the gold foil without any deviation. Without any deviation. Okay. Second one is, some of the alpha particles deflect. Some of the alpha particles deflect from some angle. Some angle. And 1 out of 12,000 alpha particles bounce back. Bounce back. Now, if according to the observation, Rutherford concluded that, what are the postulates of Rutherford? He said that, so according to the basis of first observation, he said that if most of the alpha particle pass through the gold foil without any deviation, means there is a large amount of empty space. Large amount of empty space in an atom. Okay. Second one is, some of the alpha particles deflect from some angle. So I taught you this. Positive is going to repel each other. Means if there is a deflection, means alpha particle is going to get repelled by the some of the positively charged center. Okay, alpha particle, there may be some positively charged space. Okay, then the third postulate is if 1 out of 12,000 particle bounce back, means there is a small space in which all the all positive charge is concentrated. Okay, so these are some of the postulates and the observations of Rutherford atomic model. Now, what is the drawbacks of Rutherford atomic model? If I'm going to explain you the drawbacks of Rutherford atomic model, first, what Rutherford has discovered, Rutherford discovered nucleus. As you can say, the small space in which all the positive charge is concentrated, he gave this the name nucleus. This small space he gave the name nucleus. Okay. Now, the drawbacks of Rutherford atomic model. The drawbacks of Rutherford atomic model are, Rutherford said that electrons revolve around the nucleus as planets revolve around the sun. As planets revolve around the sun. But if any charged particle revolve around the other charged particle, it is going to radiate energy. Energy is going to be released. So with that, electron in some time can be collapsed into this nucleus. Can be collapsed into this nucleus. So means with this our atom is not stable because it is going to collapse. Electron is going to release the energy, and in some time it is going to get into the nucleus only. So our atom should not be stable. Should not be stable according to Maxwell theory. According to Maxwell theory, because Maxwell said that if a charged particle is going to rotate, it is going to release the energy, and in one time it is going to collapse. But we know that our atom is stable, otherwise we didn't get uh, uh, much amount of stability. We know that our atom is stable. Okay, so there are different theories now. So we have covered the postulates of the uh, Rutherford positive charge, and most of the atom was densely concentrated in extremely small area called nucleus. Nucleus is surrounded by the electrons that move around the nucleus with high speed in a circular orbits called orbits. Electron and nucleus are held together by the electrostatic force of attraction. Now the electrons, because nucleus is positively charged and the electrons are negatively charged, so in the positive and negatively charged particles there are some kind of electrostatic force of attraction. Now the drawbacks, it cannot explain the stability. Like I told you that the Maxwell explains that if a particle is going to rotate around the nucleus, around the other charge, then the stability cannot be explained. It doesn't say anything about the electronic structure of atom, because electronic structure cannot be explained by the Rutherford atomic model. So we have covered this. Now after that, I'm going to explain you the development related to Bohr's atomic model. Now before Bohr's atomic model, Bohr atomic model is somewhat in between, but before that we got to know about the electromagnetic radiation, the dual behavior of the electromagnetic radiation. As we all know, the radiation should be wave like, okay, but this shows that electron radiation will have dual structure, wave like as well as particle like. Particle like means there is a dual nature of electromagnetic radiation, means wave like and the particle like. Now the particle like behavior is explained by photoelectric effect and the Planck's quantum theory. These are the two theories that explains the dual behavior of electromagnetic radiation. Now the James Maxwell explains some of the terms like frequency. Frequency is, for example, this is one wave. This is one wave. Now let me take this point, and from this point, how many waves are passing through this point in 1 second is called the frequency of the waves. So you are going to get a lot many questions regarding frequency. Now the frequency is this frequency is explained by nu, denoted by nu, and nu is equal to c by lambda. Nu is equal to c by lambda, and the unit of frequency is hertz or second inverse, because it is inverse of time, means the time is inversely related to the frequency. Now the second thing is wave number. Now, what is wave number? Wave number is denoted by nu bar. So, nu bar is equal to 1 by lambda, and the frequency can be related to wave number as this. Okay, now we have covered this frequency, wave number. Now the next one is I'm going to explain the photoelectric effect that is found by the Hertz, and then after that I'll explain to you the Planck's quantum theory. Now what is photoelectric effect? Photoelectric effect. Photoelectric effect. Let me take a metal surface. Okay, photoelectric effect, what does it says? For a metal has atoms. Okay, a metal has atoms. So atom in between nucleus and around that electrons are revolve. Okay, so according to photoelectric effect, if a light of suitable frequency, mind it, if a light of suitable frequency is thrown on this metal surface, of electron is going to get ejected. An electron is going to get ejected. The suitable frequency that is required for the removal of electron, for the ejection of electron, is called the threshold frequency. Threshold frequency means this is the minimum amount of frequency that is required for a metal surface to eject an electron. Okay, so if the frequency is less than threshold frequency, is less than threshold frequency, then it is difficult to eject the electron, means impossible to eject the electron according to photoelectric effect. Impossible to eject the electron. But if the threshold frequency is greater than threshold frequency, means frequency is greater than threshold frequency, then the frequency that is required to eject the electron is good, but after that the frequency first required to eject the electron electron ejection, and after that another, the remaining frequency is going to convert into its kinetic energy, is going to convert the energy into the kinetic energy of electron. Means after that electron is going to move faster with that frequency. Okay, so I can say if I am taking h nu is equal to h nu naught plus half mv square. Now, what does that mean, h nu and h nu naught? This I am going to explain in Planck's quantum theory. Planck's quantum theory. According to Planck's quantum theory, the electron is going to eject, or the light has the photons, photon particles, which has the energy h nu. Energy is equal to h nu. Light is going to eject the electrons with the energy h nu. Okay, so E is equal to n h nu. N are the number of photons, and n can be 1, 2, 3, and so on and so forth, but cannot be 1.5, 2.5. And h here is Planck's constant, and its value is always constant, like 6.63 10 raised to power minus 34 joule second. This is Planck's constant unit, and this is Planck's constant. Okay, now we have nu is frequency here. Okay, now I'm going to use this for my photoelectric effect. So I got to know that E is equal to h nu if n is equal to 1. Okay, energy of the photon particles is h nu, and this is threshold energy. Threshold energy that is required, because threshold energy is related to frequency as h nu naught, and after that half mv square is the kinetic energy of the electron. Means our h nu, the energy of photons, is going to bifurcate into the threshold frequency that is required to eject the electron, and after that the remaining energy is going to convert into the kinetic energy of the electron. I hope you can understand. So we have completed this phenomena, photoelectric effect, and the Planck's quantum theory. Now after that we are we are developing the concept related to the Bohr atomic model, and we are in the midway from this point, these points like photoelectric effect and Planck's quantum theory. We got to know that their electrons are not randomly placed anywhere, but they are placed in a particular energy, uh, the stationary orbits that we are going to say them in the Bohr atomic model. Okay, now the next are the different types of spectra that helps us to know about the uh, development of a Bohr atomic model. Now what is emission spectra and what is absorption spectra? Absorption spectras are absorption spectra is, okay, we have, suppose we have material like hydrogen gas in this, okay, and we put a white light through it. So some of the white light uh, is absorbed by this hydrogen, and they are going to excite. Now if we pass this through prism, we are not going to get all the spectra. This is an analyzer. There are some only suppose, let's suppose this one, this band, this one, this one, and this one. Suppose this is our absorption spectra. Means I am showing this on the basis of electromagnetic spectrum. Actually, electromagnetic spectrum is a continuous spectrum that we cannot distinguish in between, that where the lines are, what will be the what will be our spectra. So we use this hydrogen spectrum, and hydrogen spectrum take up the hydrogen takes gas takes up the energy from this white light and excite. So some of the light is gone. Now the emission spectra. Now we take this excited sample from here, and excited sample, because electrons now in the excited state, and they are not stable if they are in the excited state, so they are going to release the energy. So this is emission spectra, we can say emission spectra. Emission spectra, we need not to take the white light again, it already has energy, and this energy we are going to pass through the this prism, and we are going to get the lines same there. We are not getting lines here. Now we are getting lines because the absorbed energy is now getting released. Absorbed energy is now getting released. So we are not going to get this exactly same spectra. We are going, the emission and the absorption spectra are exactly opposite. Means the where we do not have the lines, we are getting lines in the emission spectra. Okay, so I hope this is easy to understand for you. Okay. Now this is our emission and absorption spectra. Now let's read it. Spectrum of radiation emitted by the substance that has absorbed energy, means already absorbed energy is going to be emitted, and that spectrum is called the emission spectra. Absorption spectra, it is like photographic negative of the emission spectra. You can say it is already it is going to absorb the energy from the white light. Now, what is line spectra? Line spectra is just like a specific amount of light that has been observed. Emission spectra, which do not show a continuous spread of wavelength from red to violet, rather they emit only specific line. Means this is the emission spectra, and the absorption spectra is somewhat kind of line spectra. This is the fingerprint reasons. Okay, now if we have taken the hydrogen gas, so Balmer, one scientist, Rydberg, explained the wave number on the basis of, let me explain to you. These are the absorption spectra. This is not the continuous spectra, this is the line spectra. I am showing this, we can show this by the line. I am showing little bit width is there, but this is mostly the line. And this one is the continuous spectra, and this one is my line spectra. Okay. Now the next ones are, now the next one are Balmer. Now I am going to explain the wave number by this 109677 1 by n1 square minus 1 by n2 square. These are the energy levels. Okay, these are the energy level. N1 can be 1 2 3 4, or N2 can be N1 plus 1, N1 plus 2. So if N1 is 1, N2 is 2 3 4 5, anything. The spectral region is ultraviolet region. Balmer, uh, for N1 N2, N2 can be 3 4 5 6 visible region. For Bastian 3 and N2 can be 4 5 6 7 infrared region. Bracket 4 5 4 N1 and 5 6 7 infrared. Means N1 is 1 2 and N2 is N1 plus 1, N1 plus 2, and so on and forth. P1 lies in the infrared region. There is another one, Humphrey, for that, and one is 6 and 2 is 7 8 9 10, and this lies in the far infrared region. Now after that, I'm going to explain you the Bohr atomic model of hydrogen and its limitation and postulates. Okay, now, what is Bohr atomic model? According to the postulates that I have discussed after the Rutherford atomic model. Rutherford atomic model, there are drawbacks, and after that, Planck's and the photoelectric effect explains that the electrons are not really move around the nucleus, like like the sun revolve, like the planets revolve around the sun. Now, after getting the emission absorption spectra and the line spectra, we have a clear understanding that there is something that we need to get good, like Bohr explained this, that electron revolve around the nucleus in a circular orbit, in a circular stationary orbit having a fixed energy, and these circular pathways are called orbits. Okay, so Bohr said that first shell is K shell, second shell is L, K, L, and after that M, third shell, and the fourth shell is N. Bohr explained this. Okay, so what I'm going to tell you, electron in hydrogen atom can move around the nucleus in a circular fixed radius, path, and energy, and the orbits are arranged in the fixed distance around the nucleus. Second one is each of these definite energies. Again, I said that, and the stationary states. Now, what we can say, the Bohr said that the energy difference between these two orbits are fixed, means delta E is always fixed. E2 minus E1 is equal to h nu. Okay, this is always fixed, so we cannot say, so uh, so if this energy uh, energy difference doesn't met, the electron cannot move from one orbit to the other orbit. Okay, the electron cannot move from one orbit to other orbit. It requires at least this amount of energy, means delta E amount of energy. If we give the energy less than this delta E, then also electron cannot move from lower orbit to higher orbit. And if we give more amount of energy than this delta E, then also the electron cannot move. So this particular amount of energy is required for, and this I can explain. Suppose I need to give 3.4 electron volt energy, or delta E, in the particular orbits in between, but I am giving it 2.3 electron volt, then electron is not going to absorb the energy and go to the excited state. It is not going to do that. It requires literally 3.4 electron volt. So the energy difference is fixed. Okay, next is another postulate is, for the electron revolve, there is centrifugal forces, mvr is equal to nh upon 2 pi, means electron revolving angular momentum is equal to the integral multiple of h upon 2 pi, and h can be 1, 2, 3 up to so on, but it cannot be 1.6, 2.6, 3.5, etc. Means decimals should not be there. Okay, so this we have covered these postulates. Okay, now the limitations of Bohr atomic model. We said that uh, there are mm, the the orbits are present in a circular in a fixed distance or a fixed energy, but the problem is when we get the hydrogen spectra, we get the some fine lines also. We got some fine lines also, and Bohr cannot explain regarding those fine lines, why these fine lines are there. If the electrons are going to move according to the energy difference, why these fine lines are there, the Bohr cannot explain. And another limitation for the Bohr atomic model is limitation for the Bohr atomic model is it only applicable for the hydrogen like atom. It is only applicable for hydrogen like atom, and which contains only one electron. It cannot explain the model regarding the two electron system or three electron system. We can say the Bohr atomic model is only applicable for helium positive, lithium 2 positive, beryllium 3 positive, means all the atoms which has only one electrons, that is going to be explained by the Bohr atomic model. So these are some of the limitations for the Bohr atomic model. Now the next one is, now what I am going to explain, I am going to explain how to write the symbol for the model. Okay, how to write the symbol for an atom. For example, I have X here. X is my element, any X, okay, element, and I have written A over here and Z over here. Now what is A and what is Z? A is mass number. A is mass number, means the mass of an element is denoted by A, and Z is atomic number. Okay, Z is atomic number. Now what is atomic number and what it is going to tell us? It is going to tell us that how many number of electrons and number of protons are there in an element. Number of electrons and number of protons are equal in the number of protons are equal in what? Are equal in neutral atom. What it is? Neutral atom. For example, I have a neutral atom like Mg. Okay, so Mg 12. Atomic number of Mg is 12. Now the number of electron in Mg is 12, and the number of proton in Mg is 12. Okay, okay. So the neutral atom and we have 12 electron, 12 proton. Now suppose if I take a non-neutral atom, or I took this positive charge over there. If I took positive charge, now the number of electrons means the positive charge means there is deficiency of electron. Means if 2 unit positive charge is there, means number of electron is 10. Okay, if there is a cation, there is electron, electron is going to decrease. If there is anion, then electron is going to increase by that charge. Number of proton remains the same, because only the electron is going to get removed, but the proton which is in the nucleus is not going to get removed. Okay, now this is for non-neutral atom, or we can say ionic atom. This is neutral atom. Okay, now what is mass number? Mass number is A, means number of proton plus number of neutron. Exactly the whole mass of an atom is in the nucleus, neutron. Okay, for example, if I say 12, 24, this is the mass number 24. The number of proton is equal to 12, because we can say this Z is equal to 12, means Z is equal to number of proton and number of electron. So plus number of neutron. We can calculate number of neutron from this. Number of neutron is 24 minus 12, that is 12, 12 newton. Okay, so I have explained to you the atomic number, the mass number. Now we are going, this is our mass number, number of proton and number of neutron, and this we have explained atomic number, types, structure. Okay, after that I am going to explain what is that is isobars. Okay, isotopes and isobars. Now you need to think about the isotopes and isobars. Isotopes which have same atomic number but different mass number. Okay, different mass number. Now you know that where it is present, atomic number where atomic number is present and where mass number is present. Suppose I am taking three isotopes of hydrogen, 1 1 1. This is in the subscript I have put 1, means the atomic number for the all the three isotopes are same, and the different mass number is 1, 2 and 3. Mass number is different for all the three isotopes. This one is what? This one is our protium. This is our protium. This is our deuterium, and this one is tritium. Okay, this one is tritium. Now the next one is isobars. According to isobars, have same mass number but different atomic number. For example, argon and calcium. Argon has different atomic number, 18 and 20, but the mass number of argon and calcium are 40. So I hope I am clear with these two terms, isotopes and isobars. So atoms of same elements have same atomic number and different mass number are isotopes of hydrogen, protium, deuterium and tritium. Isotopes, I hope you clear. Isobars, atoms of different elements with different atomic number but have same mass number, like calcium and argon I have already discussed with you. Okay, now after that the Bohr atomic model is completed. Now our next portion is dual behavior of a particle or dual behavior of an element. Means a particle should be a particle and the wave like nature should not be there, we can consider. But the de Broglie explained this, that the atom has particle as well as wave like nature. He explained this by giving an equation, lambda is equal to h upon mv. Okay, this is Planck's constant, this is mass of a particle, this is the velocity of a particle. Means he explained that a particle also has dual behavior. Firstly, rays have dual behavior, this has been explained, and after that de Broglie explained this. Now the Heisenberg uncertainty principle. Heisenberg said that a position and momentum of an electron cannot be sorry, cannot be find out simultaneously. Okay, simultaneously, because an electron is too small that if we are going to find the position, then its momentum is going to change, and if we are going to find the momentum of an electron, then its position is going to change. Like this equation, delta x delta px is greater than or equal to h upon 4 pi. Okay, is greater than or equal to h upon 4 pi, and the delta px p m delta v. Delta px is m delta v. Now I can write this m delta v greater than or equal to h upon 4 pi. Now after that, delta x into delta v can also be written as 4 pi m. I hope I am clear. Now we can read it out. Heisenberg uncertainty principle, it is impossible to determine simultaneously the exact position and the momentum of an electron. Okay, so this is our next concept, and the next one is uh, this is the basis of quantum mechanical model, that we cannot find out the exact position and the momentum, because Bohr said that the electron will be only in the stationary states called orbits. Okay, now the next one is Schrodinger equation. This is just an equation that we need to remember. H psi is equal to E psi. This is Hamiltonian operator. Hamiltonian operator. This is our wave function, energies, and from that we got the quantum number. Means the solutions of this equation are quantum number that we are going to discuss in this concept. Okay, now the principal quantum number. So the quantum numbers that they are going to explain. Quantum numbers are four types. Principal quantum number, azimuthal quantum number, after that magnetic quantum number, and the fourth one are spin quantum number. The quantum number is going to explain us the complete address of electron, that where exactly electron is there. Okay, now the principal quantum number, that in which shell exactly the electron present. Azimuthal quantum number, and then the magnetic quantum number, and then the spin quantum number. Let us see what does that mean. Spin quantum number. Okay, now the principal quantum number is denoted by n, azimuthal quantum number by L, magnetic quantum number by m, ms. Okay, let us see. This is our principal quantum number, azimuthal quantum number. Okay, if n is equal to 1, means it's a k shell according to the Bohr atomic model. L values lie between 0 to n minus 1. Okay, 0 to n minus 1. M value lies between minus L to 0 to plus L, and the spin quantum number is always minus half or plus half. Means an electron, if it is revolved in an anti-clockwise direction, then it is minus half, or if it is revolving in a clockwise direction, then it is plus half. So suppose n is equal to 1, k. Okay, now we have for the k azimuthal quantum number will be 0. Okay, because n minus 1 means 1 minus 1 is also 0. For that, magnetic quantum number is 0, and the spin can be minus half and the plus half. If n is equal to 2, so L and azimuthal quantum number will be 0 and 1, because we are going to take a break of one after the other. So 2 minus 1 is 2. So these are the two subshells. This denotes the subshells subshells, and this is the orientation in the space, orientation of orbitals in the space. Okay, so our magnetic quantum number will be 0 for this one, and -1 0 +1 for this one, because minus L to 0 to +1 with a gap of 1 1 in it. But the orbitals, the electrons in the orbitals always have the spin like -1 half and +1/2. If n is equal to 3 means KLM. Now we have 0, 1 and 2. Okay, so for that, the magnetic quantum number is 0 for the first one, and -1 0 and +1 for the second one, -2 -1 0 +1 +2 for the third one. The electron will be like this. Okay, now if n is equal to 4, KLMN 0 1 2 3, because we need to put the azimuthal quantum number to 0 to 1, 0 to n minus 1, and for that magnetic quantum number is 0 -1 0 +1 -2 -1 0 +1 +2 -3 -2 -1 with a gap of 1 +1 +2 and +3. Spin again +1/2 or -1/2. Now I am going to tell you for the different values of L what we are going to write. If L is 0, then we are going to name it as S orbital. Okay. If L is 1, then it is P orbital. If L is 2, it's D. If L is 3, it's F. If L is 4, it's G. And if L is 5, it's H. Okay. So we are going to put it. Means if for this we can say this is 1s. Okay, because 1 is for the principal quantum number and s is for the azimuthal quantum number. This is 2s, this is 2p, because s for 0, L0 it's s, for L1 is p, for this one it's 3s, it's 3p, it's 3d, 4s, 4p, 4d and 4f. Okay, so I hope you can understand that how we can use this principal quantum numbers, and this after that we are going to talk about the electronic configuration. Okay, so I explained to you regarding these ones. Now the electronic configuration, if I'll explain to you the electronic configuration. Okay, so first I'll talk to you the electronic configuration, how we can write the electronic configuration. For the s orbital, we can make a, a square box. For a p orbital, these are not the exact shape. I will discuss it with you, the exact shape. P orbitals, all the orbitals are degenerate, means for the p orbitals, these are degenerate orbitals when they are at the same energy level, and after that the d orbitals when they are at the same energy level. Okay, okay, so these are also degenerate energy levels. Okay, now what I am going to explain you, the filling of the electrons. If I'll explain to you the filling of electrons, there are three rules that we need to follow. First are Aufbau rules, Aufbau rule. Second one is Hund's rule, and third one is Pauli's exclusion principle. I will tell you how you are going to fill the electronic configuration, or how you can fill the electrons in the orbitals. So Aufbau rule means first we need to see the Aufbau rule is the ground state. Electron are going to fill first in the less energy orbital, and then coming into the higher energy orbital. Now, what does that mean? For that, we need to choose Bohr-Bury's rule. Bohr-Bury rule, according to Bohr-Bury rule, first we need to check the n plus L value. If n plus L value is less, then we need to put the electrons in that orbital. Okay, n plus L value, if we need to put the electron in that orbital. If n plus L value same, electron fill first in lower n plus L value. Okay, if n plus L value same, then you need to put electron in lower value of n. Okay, value of n. Let me give an example. Suppose 1s, 2s, 2p. Okay, find out n plus L value. Here n is 1, s L is 0, n is 2, L is 0, n is 2, L is 1. Okay, so 1 plus 0 is 1, 2 plus 0 is 2, 2 plus 1 is 3. Okay, so the lower the value of n plus L, the energy is lower, and the electron is going to fill first in the 1s, and after that 2s, and after that 2p. Now after that, if I am taking 3s, okay, so again 3 plus 0 is 3. Now the n plus L value here is same. So you need to take the lower value of n. So 2p is the of the lower energy. Now first electron is going to fill in the 1s, and then the 2s, and then the 2p, and then the 3s. I hope I am clear with the Bohr rule. Okay. Now we are going to start the filling of orbitals. Okay, after that I'll explain to you the Hund's rule and Pauli's exclusion principle with that only. Suppose I have hydrogen, its atomic number is 1. Okay, so s orbital, remember in an orbital you can put only 2 electrons. Okay, 2 electrons. Okay, now the energy order is 1s, after that 2s, after that 2p, after that 3s. Okay, then 3p. Try to do it by your own. 3 plus 1 means 4. This is greater than 3s, so 3p is of greater energy than 4s, and then 3d. Try to do this. Okay, after that, see, I have hydrogen, 1 electron over here, and so this is 1s orbit, 1s1, because 1 electron. Okay, 1 electron. Now the next is helium of the second. Now the second electron, because an orbital can have 2 electrons in it, so we have one more chance to fill the electron. So this is the denotation of electron. Now I'm going to explain you the Pauli's exclusion principle and how I am going to write this. Means I am going to put my electron like this. This is Pauli's exclusion principle, that no 2 electrons can have all the quantum numbers same. Means these are the 2 electrons. The quantum number for these 2 electrons, first quantum number is principal quantum number, that is 1. Okay, and after that s orbital, right, azimuthal quantum number, and after that magnetic quantum number is also same, 0, and after that the spin quantum number should be different. Although spin quantum number means if one electron is with plus half spin, then the next electron is with the minus half spin. So all the 4 quantum numbers are not same. We cannot put the electron with like this. This is the wrong representation for the electronic configuration. Now the next one is lithium. Lithium is 3s. Now this orbital has completed. Okay. Now 1s2. 1s2. After that I need to put the electrons in 2s. Okay. Next electron will be in 2s. Lithium. After that beryllium. Beryllium is 4, and again we need to follow the Pauli's exclusion principle, 1s2, 2s2. Okay, now the next one is carbon. Okay, carbon is, sorry, boron. Okay, boron is 5 atomic number. Now 1s2, after that 2s2, now 2p. I told you that 2p, p has 3 orbitals, p1. Okay, now the next one is carbon. Now this is easy one. Okay, but here one new rule is there. Now, what we are going to do, the next electron is going to enter in this orbital or in the same orbital. Means if is there any pairing or need to go to the next orbital? Okay. So now I'm going to explain this by Hund's rule of maximum multiplicity. Maximum multiplicity. Okay. According to Hund's, the electron pairing will not take place until all the degenerate orbitals have singly filled electrons and parallelly filled electrons. Means the electrons, see, pairing of electron in the orbital belonging to the same subshell doesn't take place until each electron belonging to the subshell is singly occupied. I explained to you. Okay. Now, so I am not going to put the electron in the same subshell, in the same orbital. I'm going to put it singly filled. Okay, this is 2p2, this is 2p1. After that, 7 atomic number. Now the again nitrogen, this one. Okay, now after that 8 nitrogen, after that oxygen. Now all the electrons in this 2p orbital is singly filled. Now we are going to pair it up. Okay, another electron, 2p3, 1s2, 2s2, 2p4. Okay, now the pairing has already done. After that, 9 fluorine, 1s2, 2s2, 2p5, 1s2, 2s2, 2p5. Okay, next one are 10 neon. Neon is 1s2, 2s2, 2p6. 1, 2, 3, 4, 5, 6. Okay, so after that you need to see the next um, orbital, next subshell, 3s, you need to consider. And I hope I am clear with the electronic configuration. So I am done with this above principle, and now at the end I am going to explain the shape of these orbitals. Okay, this is the part that I'm going to cover. So the s orbital is omnidirectional, means the shape of the s orbital is spherically symmetrical. Okay, this is omnidirectional, means in all the direction. P orbital has direction in the x direction, in the y direction. Suppose this is my x, this is my y, and this one is my z. Okay, so px will be like this, dumbbell shape. This is for px. Py, this is also dumbbell. And the pz orbital, all these orbitals are in the pz are in the same direction. Okay, means in the along the axis. Now next one are d orbitals. Okay, d orbitals. So we have 5 degenerate orbitals. 5 degenerate orbitals are like that. Suppose we have x and y, dxy. Suppose I am going to make the dxy. This is double dumbbell shape, double dumbbell shape. Okay, next one is, suppose this is yz. Now again, this means dxy is along the axis, dyz is along the axis, and dzx is also along the axis. I'm putting it like zx, okay? So in between z and x, z and x, this is our dz of, means dxy, dyz, dzx are not along the axis, these are in between the axis. But two orbitals of d, dx square minus y square are dx square minus y square is along the axis, and dz square is also along the axis. Okay, this is dz square orbital. So these are some of the I can say or shape of orbital. You can see this clearly. Clover leaf type structure, two angular nodes. So these are the spherical shapes. Okay, I hope I am clear with all the mind map questions, and you are going to get a good knowledge of this with by seeing this lecture. Thank you so much for watching.